Hello, Data Standard community. I'm your host, Shayna Weldon, and this is the Data Standard audio experience. We have a very exciting guest today. On our podcast, we have Carlos Cunha, a senior data scientist at Bosch Center for Artificial Intelligence. The Bosch Group is a leading global supplier of technology and services for smart homes and connected mobility. But going back to Carlos, he is an accomplished PhD astrophysicist with a strong background in mathematical modeling. And today we are speaking about AI techniques. Welcome to the show, Carlos.
Hi, Shannon. Thanks so much for having me.
Thank you for being here. And just to start it off, can you please introduce yourself?
Sure. So I'm originally from Brazil. I came to the US for college and I transferred here, then did my PhD. I was focusing on cosmology, so how the universe began, what it's made of. Did that for a while, did a couple postdocs. And when I got to Stanford, there was so much going on in the Bay Area, I decided I wanted to stay. So I got this job at Bosch where I'm basically a consultant in artificial intelligence, and we help all kinds of divisions of the company put artificial intelligence into their products. It's a really fun job.
Wow, that sounds great. So how did you first become involved in artificial intelligence?
So for my PhD, one of the key things in understanding the history of the universe is the fact that when light from distant galaxies travels on its way to us, it gets stretched because the universe is expanding. So the amount of stretching is called the reddening or the redshift of the light tells us how much the universe grew since the light left the galaxy. So it's kind of the key quantity to be able to reconstruct the history of the universe. And we have measurements from the telescopes, and we wanted to use those measurements to predict the redshift. So we looked at everything that we could find, and that's how I got my start. The only thing that's a little peculiar is that the light from the galaxies is sometimes up to 100,000 times fainter than the night sky. So you're completely dominated by noise, and that makes the whole thing way harder.
Wow, that's remarkable. I love learning about this stuff. I guess the next question would be, how did the AI you were doing for astrophysics compare to your role in the industry?
Great question. I think I got my job because I was handling a lot of data. We were trying to make calculations for hundreds of millions of galaxies. And in the beginning, it was around 2014, there was the deep learning revolution was well underway, and you had these great achievements in image classification with ImageNet and all those things. And it really didn't seem like it was the same thing. The new AI, the deep learning, were very powerful techniques to handle very complicated data, but with very strong signal. Images are very rich in signal. Every pixel has some information. For galaxies, on the other hand, we had almost no information, it was completely noise dominated. So I thought these will never apply. But it turns out, whenever people get a sensor, they buy a sensor, they always try to push the limits. They want to use it beyond its capabilities, get the most out of it. And then we get back to the same world where I came from, where you're dealing with super noisy stuff. So it turned out that it came full circle, and I kind of do, at least in principle, the same things that I did for my PhD, though with different techniques.
Yeah, I know you mentioned noisy data. So what can you do if you only have noisy data in a data set?
Yeah, sometimes you have to step away and do something else. But mostly when they call me is because there's a few things to try. So you need more information. And that information can come either from your prior knowledge, you have something about what you're using that makes it special. So it restricts the space of possibilities. Or something that I really like is to combine data. In astrophysics, they call it often co-adding. You can get a lot of bad measurements and they can add up to something meaningful. That's really magical. And there's no rule to how to make this happen, to how to combine data from the same sensor or from different sensors. It's a lot of art to it and a lot of creativity. So that's what excites me about it.
That is truly exciting. Yeah, and you also mentioned combining data. And when you combine data to make something greater, like cars being used for, I know they're being used for mobile weather and geological assessment stations. Like, I guess the question is, how can we combine sensor information to make something greater?
That's an excellent point. Combination comes in many forms. I think an easy one is in manufacturing. The world right now, manufacturing production is spread out over many different countries, over many different companies. And if you try to order a dishwasher today, you find out quickly that you can't, because the pandemic disrupted all these supply chain networks. But so if you want to make products better, you really want to understand the full life cycle from the product, from all this supplier network. There's manufacturing happen and users are using it at the final end. So you'd like to have measurements throughout this entire process, and you'd have companies having to share data to make each of their steps in the supply chain better. That would be really an amazing thing.
Yeah, so if there are different companies working together, how do they share data and information?
I think right now we're kind of in this age of the gold rush of data, where people say data is the new gold. And that's kind of a problem for this, because people tend to overvalue what they have. Most data is not valuable at all. It's entirely discardable. And most of it is not anything secret. So the most important thing is that companies learn to value data appropriately. They understand what value each part of their data brings to them, and what value they can sell their data to their collaborators. I think right now in the world of data, there's a lot of bartering going on. When your phone uses your location to make their maps product better, you're getting an app that works better. This is very naive. It's just an exchange. And I think in other products, data is now as a formal commodity should have a proper monetary value. And that's how people can know what they're getting and what they're buying, what they're selling in a more trustworthy way.
Yeah, moving towards the idea of artificial intelligence, in your opinion, what is the greatest limitation of this AI?
I think the greatest limitation is that it doesn't extrapolate. You really need to give every example possible of what you want so that it can make a good model. And that worked well in the beginning when you're very limited data set and you're comparing things in the exact same data set. So you can compare many models against ImageNet or against the digits data set. But what happens today is that now that you want to deploy it in the real field, in the wild, you don't have that control anymore. You will never be able to replicate two driving situations, for example, twice. And so you can't really say what model is better in a controlled way. And the topic of noise is also relevant here, because if you don't know what the deep learning models are learning, they are designed to overfit. They're designed to go after the noise. And in the wild, that can lead to unpredictable behavior.
Wow. I like the term wild that you keep using. Do you have any recent projects that you're excited to be working on?
Speaking of the wild, I've done some work in agriculture, which is the most meaningful to me. We're trying to make high precision agriculture to give plants exactly how much water they need. And that was, I think, fascinating technically, but also enormous impact, particularly here in California. And the wild really comes up. There's animals, they eat your sensors and, pesticides, and you just can't imagine how many things happen, and a simple measurement becomes like measuring cosmology, impossible. Another topic that I had recently that was pretty cool was that I got to mentor a master's thesis on the topic of hazard detection, which I found really fascinating, because in AI, normally with this training set approach, you know what you're teaching the machine to learn. You give it some objects, it learns these objects and it can detect them. With road hazards for vehicles driving, there isn't that notion. Anything can potentially be a hazard, and it has no shape, because it's debris. So you can't even try to give it enough examples. So it hits head on this problem of AI generalizability, where it has to detect that something is an object without knowing what object that something is. And it also has to deal with context, that a hazard is only a hazard if it's potentially a danger to whoever is driving. So image contains many objects that, were they in the potential path of the vehicle, would be a hazard. But if they're not, then it doesn't matter. So it adds that localization aspect to it that was also not very covered in the literature. So we got some really great results, and finally the paper was accepted last month. So it was pretty exciting. And just a quick shout out, the person who did most of the work is Simon Geisler. He's an amazing student. He's in Germany right now.
Wow. Well, congrats to him and you. Yeah, regarding vehicles and hazards, I know Bosch has a big self-driving car presence. So the big unanswerable question is, what is a good self-driving car?
Yeah, I think that's a great question. And like you said, there's no universal answer for everybody. What it means for a regulator, for a user, it's pretty much impossible to make a apples to apples comparison. And the usual bar that people set, that, no fatality, is just extremely hard to gather enough data to see a failure happen. So making controlled experiments has been the way that the field evolved for so long. And people can attempt now to do simulations, and create artificial towns where they can do all these tests. But you have the only stable thing is statistics. You assume that both sets of experiments come from the same distribution of events. And if you do enough times, then it's fair. But it's really a problem. And I don't think anybody has an answer.
Yeah, well, I think you did a great job at potentially answering it. Yeah, I will say. So We Get the Data Standard are a group of data enthusiasts and data thought leaders where everyone is open for collaboration and to connect with one another. So what can our community do for you specifically, Carlos?
I like to keep abreast of what's going on. The field evolves so fast that I find it's critical to know what people are doing and what they're thinking. And when you go to conferences, you get a sense of what the academic research is. And a more informal setting like this really gets more to see what people are doing on their day-to-day and how they're solving those non-academic problems that are really big and really interesting. Yeah, it's great to be part of this and helping the next generation of data scientists come along.
Yeah, that's correct. And yeah, great. And just for more information on the data standard, you can find us at www.datastandard.io. This episode was also sponsored by Pandio. They are innovating the tech space, and you can learn more about them and their work at pandio.com. But once again, Carlos, seriously, thank you so much for being here and for joining us.
Thanks so much for having me. I had a lot of fun.
It was great speaking with you. Thank you.